Okay. Right. So let's go to the notes. And so far, like, I'm kind of basically going over a bunch of math concepts from multivariable calculus and linear algebra just to I mean, just as good stuff before actually, like, I mean, if I'm going to use like a neural network library, like, I want to be able to at least have some understanding of like what's going on behind the scenes. So anyways, we covered 1 and 2, and then now time for number 3, which is um kind of like very connected intimately to number 1, dot product relation to projection. So projection matrices. Yeah, let's do that whiteboard thingy again. Right, so like here's a new whiteboard. Now like there's this book like like the same book I alluded to right here, by this professor. Let me just Google it. So not linear algebra's applications. That's a bit more advanced, but I think that like, yeah, this one, Introduction to Linear Algebra, like this book right here. So yeah, 20, like the 5th edition. I believe the 6th edition actually just came out really recently. It actually has like some relation to I think I might actually buy the newest edition, like right, this 5th edition, but like if I do that and then like do a 6th edition. I remember seeing something promising last week. Uh, right. Just take that and then copy it. 6th edition. Wait, what? Wait, what? 2023, right? But that's 2016, which I was like the one which I personally reviewed. Or maybe it was 4th edition, but anyways, let's click this. Right, so like yeah, this, I mean, it's kind of funny how it says like Gilbert Strength 5, but it's actually 6. That was a bit confusing to me. But anyways, yeah, his most popular book, Introduction to Linear Algebra. Right, so like when I took Math 54 in Berkeley, like it was like one of the worst classes, like poorly taught class I've ever had. Our book was, at least in my opinion, fairly useless. So I actually used like this book right here, an earlier edition of Introduction to Linear Algebra, Professor Scragg's book, and like that basically kind of like, yeah, that was really useful to me. Anyways, so like I want to buy this because of this like thing I just saw earlier. The final chapters of this edition treat optimization, learning from data, and then that like learning from data optimization, like that's precisely that's exactly what this whole deep learning stuff is about, right? So like I really look forward to like kind of rereading this whole, but I've never actually finished this book. I've just kind of like read whichever sections were interesting to me or relevant to the class I was taking, whatever pertained to that stuff. So I do want to like get this book. In fact, I'll just add it to cart. Wait, no, never mind. Actually, no, forget. Anyways, but the point is that like I look forward to reading this last section. But anyways, but back to the point. I'm basically like, what I'm going to do when I'm talking about projections, I'm going to basically follow whatever chapter that is, like in that book I just showed. Like I'm basically going to like go by the book, like my recollections of the book, and then I'm going to like add a little bit of like an extra connection, like add some nice proofs too, because like, there's another book, Linear Algebra Done Right, and I kind of want to incorporate some proofs from like that style. Like for example, like many of the introduction textbooks to linear algebra, like when they do like rank nullity theorem and stuff, like initially like there's lots of like stuff about like, like how you actually solve a system of equations, like row reduction and like pivot columns and like that type of stuff, like pivots. Whereas like it's like very nitty gritty in the details of row reduction, like pivot columns, if you're trying to prove the rank nullity theorem. But like I like to think of things in terms of like the actual basis vectors, and there's like there's some proofs that like kind of rely on like pivot columns and stuff, but like it's really neat to like kind of circumvent that because anyways, I digress. Let's just go back on topic. So like here's like the two main things that are kind of going to be done. One is, let's say we have, sorry, I'll undo this. I'm going to deliberately make this one small, right? So let's just call this vector A, right? Just a vector. And now we have a vector B that's intentionally longer than A, right? So now what I want to do is I want to look at span of A, right? So what is span of A? Like visually, it's just like an infinite number line, an infinite line, right? So like span, let's just give these two hats. So then there's like, so what I want to ask is if we project B, right? Like let's take span of A, which is like dot dot dot, like this wait, sorry. There's no arrow here. What am I doing? This is basically like a, not a number line, but just a single direction, like basically a line, like a whatever you call this, like it just starts from here and it just kind of goes for, I mean, yes, it actually could go here if the coefficient's negative. What am I talking about? Yes, it is a line, a number line, or it is a double, it is a line that just stretches on forever in both directions, right? So now what we want is, what I'm asking, like, what is the projection of B onto not A, but span A. That's a crucial distinction. Now, when I was actually talking about like dot product relationships to projection, for most of like the stuff I was like kind of blabbering on about, I was assuming that we were dealing with unit vectors. Like A and B were both unit vectors, so like projecting one onto the other is kind of the same thing. Like there's no need to like kind of specify that we're doing the span, because because here we need the span because like B, if you like drop this perpendicular right here, right? Like this we just drop a perpendicular right here, and like we basically want to like solve for this because like kind of if you drop the perpendicular, then like this vector is kind of greater than A, right? It's like kind of the magnitude is larger than A, right? There's like a scaling factor that kind of scales A by a bit greater than 1. Whereas if they're both unit vectors, then we know that that can never happen. But anyways, what we basically want to find is like this vector right here, right? We want to find the projection of B onto span of A, right? And then like this is pretty easy. Like this should pretty much be kind of quite simple based on just based on like this dot product relation to projection, right? So here's how I would do it. Like this is not how the book does it. So I'm just gonna like, just draw this theta here. And then what do we know? We know that A transpose B, or A dot B, right? A transpose B. Well, I don't like drawing the transpose. Let's call this A dot B. So we know A dot B is equal to the magnitude of A and the magnitude of B in cosine theta. But I'm going to rearrange it to actually let's just kind of take this. No, forget it. Magnitude of A, magnitude of B, and cosine theta, right? Actually, before I do that, I'm just going to briefly like kind of on the side, like we're going to solve this problem right now, but then what we're going to solve later, which is like the actual interesting stuff, especially for like the general case, is we have like A1, A2, right? And now we have some B here, and then like we're basically like kind of solving this simple question to like lead up into this greater question, right? And what we want to do is we want to like solve the projection of B onto like like we want to solve the projection of this B onto the subspace of, let's call this, actually, why am I making superscript? This should be subscripts, right? So we have like A1 here and then A2 here. So then span of the set A1, A2, right? Span of the set A1, A2. And of course, we're going to generalize this for like AM eventually. Like the same principles apply. If we can do it in 2 dimensions, we can do it in m dimensions. So we want to find the projection of B onto span of that. And that's like what we're going to like kind of eventually do. But for now, I'm just like starting with the easy case where we only have like one vector, like just A1 or just A. Like there's no like A1, A2. It's just a single thing. So we know that A dot B is just AB, magnitude A, magnitude B, cosine theta. So B cosine theta right here, like if we were just to like treat it as like a simple right triangle, right? Where like this is the length of our answer. Let's call this like let's call that P. Like, let's call this desired thing P. So this is going to be like the length of P, which we want to, like, this will be its magnitude, right? Like this length right here, like what we want to do is we want to get this vector right here, which goes from this point origin to where the perpendicular drops. And that's P, what we're trying to solve for, right? So P's magnitude, like, we have kind of this right triangle right here, right? Right there. Like, that's the triangle which which this thing right here signifies. So this is 90-degree triangle, and then this right here, the length of the hypotenuse is B, right? So AB cosine theta is this, right? So instead of A, let's just call this PB, P dot B, P. Sorry, what am I doing? This A. I like how like the circle in the A becomes kind of a circle in the P. But anyway, so this B cosine theta right here, this length is but the this PB. Wait, no, what am I doing? This is A. Let me just undo everything. Right, so B cosine theta right here is the magnitude of P that we want. Right? Like, we have A, we have B. Like, we know A, we know B. And from that, we can get, like by dotting them, we kind of get some information on B projected onto A. Namely, we get its length times the magnitude of A. So then B cosine theta, magnitude of B cosine theta is P, right? So let's just make that equal to A. Let's just actually do the substitution. Magnitude of P, right? So what is the magnitude of P? So the magnitude of P, if we just kind of divide both sides by magnitude of A, right? So magnitude of P is A dot B right here, the left-hand side. So we're taking this, we're dividing by the magnitude of A, we're dividing by magnitude of A to cancel that out, to isolate what we want. This, right? So this is the magnitude of, like, so like P is right here, right? We know its magnitude, and a vector is just two things, like a direction and a magnitude. So here's the magnitude, and now we just need a unit vector in the direction of, like, this line. So like P is just equal to what? A magnitude times a unit vector, right? The unit, like, let's just normalize A. Then P, which we want, is simply the magnitude of P, that is this thing right here, times a unit vector in the direction of A. So we can just compute this unit vector by just doing this. I mean, that's how we just normalize A, and that is P. So then P, to recap everything, to like solve the answer, P, the projection of B onto span of A, is A dot B over, like, you have, like, you plug this in over this thing squared, because you have one in the bottom and another in the bottom, so that's two in the bottom. The squared magnet, yeah. And then this whole thing is it's like a scalar multiple. Everything here is scalars times A. And this right here is our answer, right? Now the question is, how would I go about doing this, right? Like, would I use kind of the dot product of B and A1 and B and A2? And, okay, I'll just give you a sneak preview of the answer. If A1 and A2 are orthogonal to each other, right, then we could just take the projections of B onto both of them, add them up, and that could be our answer. But in the general case, A1 and A2 might not be perpendicular to each other, right? Like, we could use Gram-Schmidt, which is like a way of taking a set of bases and orthonormalizing them, and then we could do it. That's a lot of work, right? So I'm going to first of all, like, so there is like a nice little trick that the book, which I mentioned, does it. So I'll first like use that trick on this simple case, right? Projecting B on span A. So what it basically does is, let me just redraw this again. B, and that's A. and then like this whole thing going forever in this direction is span of A, right? Just keeps extending. So now it basically says that like, let's split B into two components, right? We're going to drop like this thing which we dropped down, we're going to call this the error vector, E. E is in the left. Okay, so like we have this error vector right here. And then this is our desired vector right here, which we want to solve for, P. Right? So what this book does is it basically like decomposes B, which we like the thing we're projecting onto span A, into what we want, P, plus E, right? Now, furthermore, it does another thing. We can express P as what? As the vector A, right? Times some scalar, because like, and we can call the x hat, and that's pretty intentional. This hat notation for like how much we're scaling A. So like, why are we introducing this, right? Like, what is P? Like, if you look here, right? Like, this is A, and then P kind of takes A, but it goes a bit beyond. So like, any vector on span A is basically like the definition of span A, in fact, right? Is like all the scalar, like the subset of like all the scalar multiples of A. And 0, like including 0. Like, so like we like 2A, 3A, 4A, 1.5 times A, like these are all in span A. So P is just some scalar multiple of A. So let's write that out, right? Let's just plug this in. X hat A plus E, right? In fact, let's just set that equal to B, right? Let's just so this is what we have so far. Like we're working with this right here, right? In fact, let me just, anyways. So now what we can do is take this whole thing, and then, now this is a very obvious operation, obviously. Let's just dot both sides by A, like A transpose. Let's just dot everything by A, right? So from linearity, what do we have? Now, I remember like in one of my like previous kind of videos, I mentioned if like taking like this common pattern of like dotting both sides by something to zero out the perpendiculars. Like that's like a pretty kind of common nifty little trick that I've seen happen a lot when dealing with orthogonality. So what does the left side become? Now x is a scalar, right? So we can just kind of move that to the left. So this underlined thing, if we dot both sides by A, we basically get the scalar kind of comes out, right? And then this A dot itself just becomes this thing right here, the this thing squared, right? Because like cosine of that is 1. And here's like the key moment. A dot E, right? This is A and this is E, and they're perpendicular, which means like, as we know from dot product relationship to projection, that means that the dot product, that is 0. Like this whole thing zeroes out. So then the right hand side is simply just A dot B. That's it, right? So then we can divide both sides by magnitude of A squared to isolate x hat. So x hat, right? X hat is equal to A dot B divided by the magnitude of A. Yes, I'm not writing those vector symbols. We know that A and B and E are vectors. Actually, yeah, whatever. A. So now we've solved x hat, right? So we know P equals x hat of A. So like that's, and now we've kind of defined, like we've derived like what the scalar is. So we just kind of plug that in there. And what do we get? Well, we get the answer we're looking for. P equals, and now add the hats because, well, I mean, I'm kind of presenting a pretty result here. and this whole thing is our scalar. So let's just kind of wrap that there and multiply that scale A by that much. And that's our result, right? That's another way of doing it. Like I did it right here. I got P right here as A dot B divided by magnitude of A squared. That whole thing's scalar factor for A. And this is the exact same expression, except like it uses like this splitting B up into like different components, the projection and then the error, and then this, and like kind of leveraging the fact that if you dot product by A, then like this term zeroes out. Now to solve the more general case, we actually have to like at least I'm not sure we have to, but like that's the technique this book uses, which is a really nice technique, right? So let's do that right here. So let's just call let's just this is our answer, like what we want right here as P, right? And then let's kind of exactly what we did before, E, right? So now B equals to P plus E. Now the question is, what is P, right? Like previously P was P could be written as a scalar multiple of A, right? But now like but now what is A? Like what's the analogy here? The analogous thing is A1, A2, right? So like first what we had here is kind of like X1, A1, right? So now let's kind of like let P equal to like X1 hat, I guess. X hat 1 A1 plus X hat 2 X2 hat A2, right? Now this is a very kind of like crucial, like this is a crucial moment here, right? So like here we did P equals to some scaled thing of A, right? Like we're given this kind of number line span A, and then what is X hat? Like it is, if we kind of like add like numbers here to make it an actual number line, that X hat is the coordinate, right? Similar to here, if we have like now like A1, A2, like these are both number lines, we go like, and then to get P, we go like X1 distance in this A1 direction, and then after that, or sorry, maybe we go like X1 distance here, like we go X1 distance along A1, and then we go like we might go X1 distance here along A1, and then we might go X2 distance along A2 to reach P. So just like how I guess I can't. I want to delete. Wait, no, there's nothing to delete. So this is like a crucial relation right here. Like in this single dimension case where we only had just one A, not A1, A2, X hat was how much like the coordinate along this A axis. It's how much we scale like. Okay, technically it's not like a coordinate. Like it's only a coordinate if A is a unit vector, but it's basically kind of like the coordinate with respect to this basis vector A. It's like the coordinate for this basis vector A. And now like basically like in this case A1, A2, right? They're basically like the span of that is a subspace where like A1, A2 are basis vectors. So any vector in the subspace of A1, A2 can be represented as a linear combination like of these basis vectors. Now this right here, if you're familiar with like matrix notation, and this is the key part, right? This is where like we get actual project like matrices. So this is A X hat, where A is just like we concatenate like the columns like A1 and A2, right? Those are our two like basis vectors that like specify like that, yeah, our two basis vectors, and then we're kind of that's kind of like we're doing that to left multiply X hat, where X hat like that this whole thing is A, and then X hat, right, is X1 hat, X2 hat. So what is the significance of like this x? What is the significance of x hat, right? It's basically like the projection, right? The projection of B onto the subspace that is span of A1, A2 is P. Like we want to solve P. Now this P lies on this plane, like the plane that we like that A1 and A2, like A1 and A2 are basis vectors and they can kind of specify a plane, right? And that plane is like the geometric interpretation of the subspace, the span of A1, A2. And any point that falls in this plane can be represented as like some way of some linear combination of A1 and A2. So basically, I think of x hat as like the coordinates of like how much of A1, how much of A2, like how we the ratio, like how we blend A1 and A2 to get P. Like if we actually if we actually do this multiplication, like right, like what is this like matrix thing like actually do? Like this A1 kind of goes into that, and then x1 and x2. So x1 goes into that, and then x2 goes into that, right? So like if you actually write this out, this actually ends up like being like x1, I guess, hat times a1, right? A1 is the vector plus x2 hat, right? This is x2. Basically, the point is, by actually multiplying like matrix multiplication, one way of viewing it is like we take these columns and we weight them by these. So basically, if you actually multiply them, this multiplication results in like this underlined equation right here. So let's just take this. So now that we've kind of established like how the analogous kind of plugging in like P equals x hat A, like we can kind of like generalize that in multiple dimensions. So like long story short, we just put this in here, we do the exact same thing, right? So what does this get once we plug that in? We now have B equals to A x hat plus E. And now, naturally, this is very obvious to everyone, I'm sure. We're going to take everything here, and just like we like kind of did A transpose, we dotted everything by A. What we're doing now is we're instead of A, we're kind of having like the more general A, which is now like we're transposing A, and then we're matrix multi, like we're just kind of applying AT to B and then kind of that and that, right? So like basically what this is doing, like after we apply this A transpose to both sides, we get ATB. Don't worry, I'm going to explain the motivations behind this. ATB B equals AT A x hat, right? Plus, and we know what's going to happen, ATE, the kind of the error, like the difference between the projection and like B, like, so now this thing zeroes out. That's the geometric kind of idea right here, like how like A dot E equals 0, and we were able to like just kind of zero this thing out, right? Like we just got this and we got that. Like we kind of A dot E was 0, right? So basically ATE, like what, like 0, basically we're saying that this E, right? This E that we have here, like that's like kind of splitting B into like that which is on the subspace, and then like the kind of the perpendicular extra stuff, like, so this extra stuff E that's kind of like pointing in the perpendicular direction to the subspace, like, is in the left null space of A. So like if you look at AT, like what does AT like transposed actually mean, right? So in our just two-dimensional case, AT looks like this, right? It has like two rows, right? A1 and A2, right? So now like when we actually like kind of like take, like when we have like E, right, as like our column E vector, then like this will be like if E is like a 2x1, because we have like A1, A2, let's just, the point is that like there'll be some entries here, like some entry here, some entry here, and so forth, right? So now, like, let's look at this entry, right? This entry in matrix multiplication is you take this column, like you take this column and you dot it against this row, right? So this entry right here is A1 dot E, right? And this entry right here is A2 dot E. But in the geometry, right, we know that this E is perpendicular to this entire plane. Therefore, that means that E is both perpendicular to A1 and is perpendicular to A2. It's perpendicular to the whole subspace generated by A1, A2, so that's 0. So this whole thing like equals like the 0 vector right here, right? So this whole thing zeroes out. Okay, so now we just have this thing right here. We just have like this, now we're just kind of working with this equation, right? So then we do the same thing we did there. We solve for x hat, right? So then let's invert, like let's solve for x hat. So what is x hat equal to, right? So x hat equals to what? X hat, so like we have to get rid of this. So let's like kind of take both sides and then kind of do the inverse of whatever it's, take this stuff and invert it, right? So you have AT, this is, I don't need to spell it out. I'm just gonna write this directly. So we take AT, and how do we move it to the other side? Well, we just take the inverse of it, right? So that's AT of A, and this thing gets inverted, right? AT of A gets inverted, and then ATB. Yes, this looks like a lot of A's and T's, and then it's a whole mishmash of these. So you know what? Let's add another A, right? Because like P, our answer, right? P equals to A x hat, right? But we just solved x hat. So our final answer, P, and this is obviously makes complete sense, right, to everyone. I mean, it does. It actually does to me. But like, A, don't worry. I'll this is not like, don't be too. I mean, this is a bit intimidating, but like, it's there's some neat thing I can show about this. -1 A T. Yep, lots of A's and AT's going on, right? But it's okay. We'll be fine. And this is our answer to I'm so lost. To where's the question? I didn't write it out, did I? Basically, this is the general answer. Like, this is a general answer for like projecting B onto not only A1, A2, but just like all the way to AM, where we have M basis vectors onto any subspace, right? Now this should look a lot like this. Like if we compare this box right here with this box right here, right? Then like what do we have? We have a squared in the bottom, right? Like the magnitude of a squared in the bottom. And that's a lot like ATA -1. That's kind of like -1 is kind of like 1 over like division, sort of like, I mean, it's not really, but I mean, I to be honest, like this is like kind of like what the point is, like there is some similarity between them, right? Like AT and then ATA kind of is analogous to this right here. And we have like B and 2 A's. And again, we have B and 2 A's, right? Like ATB is kind of like again, it's kind of like when you actually do it, it's kind of like dotting, like AT transposed B is a lot like dotting like B against like the entries of ATB, like we saw for like the error vector getting zeroed out, is basically kind of analogous to doing A dot B, which is right here. And this whole thing by A, again, is kind of like that, right? So one thing, so like this is a very kind of really neat equation, and I'm going to talk about like how I would personally kind of understand this, right? Like in a specific case. So like this, at least here, I kind of like showed using his like the books method, the MIT math books method, and then also like my own method, like which I believe almost everyone else would do. So now like how do we go from here to here, like without using like this very like this kind of like this trick for like kind of left multiplying by AT? I mean, but by yeah, just applying A transpose to everything, this equation on both sides. So like one thing I'm gonna say is like if you actually look at this kind of term right here, right? And then let's say that A can be represented as like the columns of A are orthonormal to each other. Then this expansion right here just becomes the identity matrix I, and we can get rid of it. So like actually I'm just gonna be honest, I'm just gonna like show a Google Drive. Basically like actually there's like this drive.google.com, right? Wait, never mind. I will show it later. There's like these kind of like files that I'm like I have like my own notes in a Google Drive that I've like kind of closely following. I might just like post them later, but anyways, the point is that like one kind of suggestion I have from going from single dimension to 2D is like if let's say A1 A2 are perpendicular, right? Like if we have A1 here as like just like say the x-axis and then A2 as like the y-axis. In fact, A1 and A2 could just be I hat and J hat, right? Or like, well, let's just draw it differently, right? Let's just draw it a bit different. Let's draw it like in a plane, right? And these are perpendicular. Yes, they don't look perpendicular. That's because like we're kind of viewing it in 3D, right? And that's kind of our z-axis, right? So now if we like take some like kind of point, let's say like kind of like right, let's say we have like A1, like let's say a unit vectors, who cares? Like let's say we have like A1 plus A2, right? That's kind of like it's on this plane right here. Let's just add some like filler E, right? E right here. And let's call this and that's right here. This is going to be our B, right? So the projection in this case of B onto this plane but given by A1, A2, like in this case, like P equals to like 1 of A1, right? We go along this way, we take 1 of A1 and then like 1 of A2 is a A1 plus A2. That is our x hat is simply 1, 1. We just take 1 of each and we blend them in an even 50-50 ratio, right? Just kind of like a 1, 1. No big deal, right? Now the question is, what is the projection of B onto A1? Right? Like what is like what is the projection of B onto A1? Well, the projection of B onto A1 we can kind of use by this dimension. Like we can just use by this and replace this A by A1, right? So projection of P onto A1 is simply A1. In fact, like if we actually work this out, like if you like replace A with A, like if you do like take this formula right here, P equals to A1 dot B over A1 squared. This whole thing, A1. Yes, and I'm assuming, let's assume that A1 and A2 are I hat and J hat. That is the orthonormal. So this thing basically just simply the identity matrix. So all we're left with is A1 dot B as our scalar multiple for A1, right? So what is A1 dot B? Well, A1 dot B in this case is A1 dot B. Okay, so yeah, I know. So we have P, right, is A1 plus, like we have P as A1 plus A2, and then like B, right? B equals to P, which is A1 plus A2 plus this whole thing is like kind of P right here plus E, right? This error vector, right? So now if we do like, if we kind of dot everything, like let's take this whole thing and let's dot everything by A1, right? Then we get A1 dot B equals to what? A1 dot A1, which is just the norm of A1, right? The squared norm of A1, right? Squared. And this is the nice part. Since A1, A2 are orthonormal, I mean, are ortho, like the ortho part, right, are perpendicular to each other, this zeroes out, right, plus 0. And then same thing, A1, E are perpendicular plus 0, right? So A1 dot B is simply equal to A1 squared, right? So wait. So A1, and then A1 is the identity matrix. Or wait, no, what am I talking about? Sorry, I'm being stupid. So if you like go back here, right? And we just do like P equals to A1 dot B over A1 squared A1, right? Then we've just shown that A1 dot B is equal to that. So we can take this and plug it in right here. So P equals to A1, right? So the projection of B onto A1 is just A1. That's it. And the projection of B without loss of generality onto A2 is simply A2. So in the general case, if A1 and A2 and like if we're projecting B onto just like the span of A, like in the more general case, B onto span of A, where like A is just like the A is just like kind of A1, then like A2, the range of A, sorry, the range A2 dot dot dot. Okay, so m rows, n columns, so then n, so n dimensional space, an, right? And if we know that, like, let's just call them orthonormal, and then ai, or like, yeah, the set, like ai, the column vectors, the basis vectors that define the subspace range A are, well, or ortho, let's just say orthonormal. They only have to be ortho. The normal is just like, just because orthonormal is cool, but like just the ortho part matters most. Orthonormal, then the projection of B onto A, and onto the range of A, is simply the sum of the projection of B onto A1 plus B onto A2 dot dot dot, like just the projection. The answer is simply the projection over I. We're summing over all the column vectors. The projection of B onto AI, and this really cool thing kind of holds only if they're only if these are orthogonal to each other. I've kind of given some intuition just now, like just now, like I know I just did it somewhere, like right here when I kind of showed that the projection, like the projection of B onto each of like A1 was just A1, like cause and it's true, like we just kind of basically like this, like the answer P that we're looking for when projecting B onto A1, A2 if they're perpendicular, right? This projection is some combination of A1, A2. It's some like contribution. That's the idea. Since these are orthogonal, we kind of take like the projection has like this projection P right here, which is this arrow, is kind of like a contribution in the A1 direction and contribution A2 direction. That's what X hat kind of shows, their contributions, like A1, A2, and like we're kind of rewriting P, in fact, as a sum of the projection onto A1 plus the sum of projection onto A2, and like that's kind of like really cool that we can decompose the projection itself. And again, this only holds it orthogonal. Why? Like, I mean, I can prove a counterexample right now. Like, let's say A1 is like kind of here, right? Like kind of like the x-axis, and then A2 is like at 45 degrees, like, right? So then like, and now let's choose a B such that like this thing does not hold. Well, what if B is just A2 itself, right? Let B equal to let B equal to A2. So what is the projection of B onto, like, you know, the subspace, the span of A1, A2? Well, span of that projection simply A2. Like, if you project this onto the plane, well, it just gets this, right? But now if we try to sum it up, what's the projection? Like, we want to like say, hey, like we can take B and we can project it onto A2 and we can project it onto A1 and add them up. Well, the projection of B onto A2 is simply A2, right? But the problem is when we project B onto A1, since this is not 90 degrees, like we are going to get something non-zero, like some epsilon, like some non-zero thing, like some vector k, which is non-zero. So we have like A2 like plus some k, which is not zero. Like it would have been zero had had A1, A2, and A1 been perpendicular to each other, but it's not. So like we have this. But this is not like, but this thing is clearly not equal to that, right? Like A2 is not equal to A2 plus K. That is like where A2 is the projection of B onto like this plane, but then the projection of B2 onto each of the basis vectors summed, like it no longer holds because this because we have K, right? Like the projection of B onto A2 is A2, but sadly when we project B onto A1, since A2 and A1 aren't orthogonal, there is some component that we get, like namely something that like this, which is K, which is non-zero. So that messes things up, right? So now like let's pretend that like the AIs are orthonormal. Then we can go back to this actual case, which I was gonna do, and then like A can basically like so what is ATA, right? Like what is this like thing if all the columns of A are orthonormal to each other, right? Then like AT.A, right, is basically kind of like A1. Like AT is just like A1. Let me just write out AT. So like we have AT, right, as like kind of A1, A2, and so forth, ... whatever. That's AT. And then we're kind of doing that on A, right, which is A1, A2, and so forth, right? So now let's look at like this column and this row, right? So then when we actually expand the matrix multiplication, what's like the top left entry in the answer, right? That's this column and then this row. So A1.A1, since they're orthonormal, that would just give us 1, right? Likewise, A2, now if you look at like, so this is just 1. Now let's look at like the one right here below. That's also 1 because A2 itself is orthonormal, right? So it's just 1. And so forth. We just keep getting 1s, right? And now, what are these? They're just 0. Why? Because like A1, right, every single other number is A1 dotted against something else, but they're perpendicular to each other. So this whole thing right here becomes identity matrix, right? And if you invert it, that's just identity matrix. So in the case where the columns of A are orthonormal, we get a reduced expression P equals to just simply like the middle stuff kind of becomes identity, so we kind of eliminate it, and we get this, right? Now this is really nice. Why? Because like what I said right here, where we can kind of just sum them all up, well, this is in fact a compact representation of that same statement, right? Why? Because AT.B, right, if you look at like AT, which is like A1, A2, and so forth, against B, well, the result is going to be like a vector where like the ith entry is AI, like ... AI dotted with B, right? It's like A1B and so forth, right? So A1.B, and since A1 is a unit vector, like these are AIs are just orthonormal to each other, so they are normal vectors. So A1.B is kind of like the projection of B onto A, like AI.B is like the Namely, it is the length of the projection of B onto AI, right? Wait, what am I talking? Wait, sorry. AI dot B. So the dot product relation to projection is like AB cosine theta. So then, but then A is 1 because like the magnitude of A, magnitude of B cosine theta. So magnitude of AI is just 1, so that cancels that. We can just remove that. So AI dot B is simply the magnitude of B times cosine theta, which is the projection of B onto AI. So AI dot B, what this means is xi hat, right? Right? That is the idea. That is this thing right here. So AI dot B is kind of like the length of the projection of B onto AI. So if we have like AI, like A1, and then we have like, which is a unit vector, and then we have B, then when we actually take the dot product, we're going to get the length of this vector. That's what this entry represents. Now, when we take that length, and then we kind of like, when we do A, when we take A, right? And we already expanded A to B. We know it's just equal to this, right? We take the matrix A, which is the matrix of A is simply like A1 dot dot dot, like A2 dot dot dot. Or like A1. Let's just do like AI, like dot 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 AI, right? Sorry, this looks really ugly. Let me just undo a bunch of stuff. So A1 dot 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 AI. Yeah, a lot of this is just like kind of managing, like fudging around indices. Like that's a lot like matrix multiplication. Like when you first learn, you're like, wait, why on earth am I taking the jth column and dotting it against the ith row? Well, I mean, see linear algebra done right if you want to know that, I guess. But anyways, so like here, like A1B. I drew the one too long. A1B dot 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 A I B dot dot dot. Again, I'm just like taking ATB, we know is this, and like A is there. I'm just kind of like plugging that back in. So this final thing gives us a vector, right? So basically, like this entry right here gets applied to this entry right here. So this is like how much we're weighting the AI thing, right? Like this applies to this. So this is basically like the sum over I of A I dot B, which is a scalar, times, which scales AI. And this representation right here, like this is our actual P, right? This thing right here, like after like kind of expanding out, like writing everything out, we get this. And this thing right here is basically a compact representation of this statement right here, right? We're summing or I the projections of B onto AI. Like, what is the projection of B onto AI? Well, I maintain that it is precisely this right here when the AIs are all mutually orthonormal to each other. Because the projection of B onto AI, right? Like, the projection of B onto AI, we simply kind of know that right here as this. So, like, if we have, like, A as AI, right? Then that's AI dot B and AI. And this thing, it's just the magnitude of that is simply 1 because it's normal. Squared is just, like, 1. So I've just shown this to be true, right? So that's really cool. In fact, I think that's probably a good place to stop. Is there another way? I believe there's, in fact, like a few years ago, I actually looked at this and I kind of like did I did something else too. Like I was like, not only like this is like kind of the orthonormal case, but like what if instead of orthonormal, like normal, it's instead just orthogonal to each other. Even then, I believe that like this thing holds true, and I can actually attempt to prove it, right? So if we're projecting B onto the span of, at this point I'm getting so tired, of A1 dot 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 AN, right? And AI and like these AI, right? And these AI are mutually orthogonal to each other, right? I maintain that like the projection of B onto this is again the sum of the projection of B onto AI. Yeah, now let's go back here. I just take like this, let's just cross out the normal. And can I prove that, right? So whatever P is, right? P, the projection of B onto the span of the AI, is necessarily like can be expressed as some weighted combination. I'll use like W1 A1 plus dot 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 W n of AN, right? Like we can express P in terms of like this right here, W1 A1 dot 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 plus WN AN. So like that's kind of like where the W's are, the WI are kind of the entries in our X hat, right? So this like P is this. So can we show, all I want to show right now is that W, like one other thing, like since all the AIs are linearly independent, right? They're each orthogonal to each other. They each kind of like stretch in a different direction that's perpendicular to each other. They're not necessarily normal. They could be non-normal. They could be like magnitude 2 or so, like not necessarily 1. The point is that they're all orthogonal to each other. And then what I'm trying to show, I want to show that the projection onto AI, projection of B onto AI, let's call that like PI, the projection of B onto AI, is going to be equal to WI AI. That's the desired outcome, right? Basically, I'm expressing this projection as sum of all the constituent projections, like all the contributions from the AIs. So how do we how would you actually do that? Well, if you look at, so like the idea is like we can do that loss of generality. We can take this expression right here, right? And this kind of like the same trick which I did in the beginning. Like you just kind of take the whole thing. Let's just take A1, right? Let's kind of take this whole equation, and what we can do is we can like obviously like do the A1 transpose, like left multiply, like do that to both sides. So we get A1 transpose this projection equals to, again, the scalar, we can take it to the left. W1, this is just A1 norm squared, plus, and this is the crucial thing, like I said, like ortho, right? Ortho to each other. So every other term zeroes out, like plus 0, and so forth. So we're just left with this, right? So A1TP equals W1 of A1 squared, right? So like, and we can like, we just did this for A1, but in general, we could actually like do the same exact thing for any AI. So AI dot P equals to WI of, and then A1 squared, AI squared, sorry. So what is WI, right? So now we know what WI is. we can isolate that. Wi equals to AI dot P over AI squared. But doesn't this look familiar? This magnitude squared. This Wi, right? If we look at that, and we kind of look at the beginning case where we're projecting B onto a single line or single span A1, then this thing right here, right, P equals to A dot B over magnitude of A squared times A, like the stuff that's in the parentheses here is simply, where was I? Right, was this. Right? So we're actually done. Like what I've just shown right now is P can be expressed as the sum, P can be expressed as the sum over I of WIAI, right? The sum over I of that. That is the sum of A. So P can be expressed as the sum over I of WIAI, right? P is just this like a weighted combination, but what are the actual weights? Well, this is the actual weight we can plug in right there. And we got Wi by kind of like doing the trick where we kind of left transpose multiply both sides of this equation, like for A1, A2, whatever. Like the whole idea is for AI, by doing AI transpose against this kind of isolates the WIAI term, and everything else zeroes out as a result of orthogonality. And now we just plug that in there. So like P equals to the sum over I of all this, which, in other words, by plugging in Wi, right? By taking this and plugging it in there, is just AI dot P over AI squared P. So P, this projection, is simply the sum of the projections of P onto all the AIs. And that's a really nice result. Wait, I wanted to show that so that's it. So what is P again? P is the projection of B onto the span of all the AIs, and that we've just kind of like this means that it can also be expressed as a sum of like, okay, so technically we don't want this P here. We want it to be B, but like we know that P, like B equals P plus E. And like whenever we like do a dot product, like whenever like P plus E, right? But whenever we do any AIs dot P, right? Like necessarily like AI dot B equals AI dot P, because like everything else zeroes out. Actually, I think I'll basically stop right now, but the whole idea is that like ultimately there's like only one thing that really matters, and that's this thing right here, right? This whole thing can be called a projection matrix, which like takes B into like, and then when you multiply by this whole jumble of A's and AT's and this negative, this inverse, you get the projection of B onto this thing. And there's a very kind of neat, nifty idea where if A's are, the columns of A are orthogonal to each other, then like this whole thing, kind of this middle term becomes identity matrix, and if they're orthonormal, becomes identity matrix, and we can easily kind of understand this in a very kind of compact definition, that there's like basically like if these are kind of the columns of A are orthogonal to each other, then we can kind of view this as the sum of like the projection itself is a sum of the projections of B onto each of those AIs. I'm not sure I exactly prove it, but I mean, the strategies I use could definitely be used to prove it. But ultimately, like, this result really matters. And next time I will discuss very, very briefly that, like, again, we have an inverse operation, so I'll kind of make sure that we can do this inverse. Like, that is, this only works if A is linearly independent. Like, all the columns are linearly independent. But I'll talk about that next time. But this is the main result we have here, just the projection matrix. And then when we're doing least squares, we'll basically just be using this. So yeah, I think that's all for now.